Okay, welcome. We're just about to start the type session. Okay, great. So it's my pleasure to introduce our first speaker for this session. So this is Mickael Laurent, who is coming to us from Paris, from Universite, and he will be talking to us about type cases, union elimination, and occurrence typing.
Thank you, Stephanie, for the introduction. Thank you, everyone, for being here. I am delighted to be here to present you our paper. So it is called On Type Cases, Union Elimination and Occurrence Typing. And this is a joint work with Giuseppe Castagna, Nguyen, and Matthew Lutze. So let's start with some context. Here is a function in JavaScript. It tests whether its argument is a number or not. If it is a number, it does x plus 1, otherwise x.trim, with trim being the method that can be called only on strings. So JavaScript does not provide static type checking. So if we want to type check this function, we have to use a language such as TypeScript or Flow. In this case, we add type annotations. We will say that this function takes as input either a number or a string, and it returns either a number or a string. So what we want to do is a type system that is able to type such a function. In order to do that, the type system must be able to refine the environment when typing the two branches of the type case. So for instance, when typing x plus 1, it has to remember that x is a number. And when typing x.trim, it has to deduce that x is a string. This is called occurrence typing because the different occurrences of x are typed differently, depending on the branch in which they are. We also want to have expressive types. Here we just said that this function takes either a number or a string and returns either a number or a string, but we can be more precise by saying that when we give to this function an integer, it returns an integer, and when we give it a string, it returns a string. Also, we would like to have type inference so that the user do not have to write these type annotations. The user just writes the unannotated function as in the JavaScript, and the type system will infer them and check them. Also, we wanted to work for test with arbitrary expression. Here, we just tested whether a variable has a given type. But for instance, we might want to test whether the output of an application of a user-defined function gives some types. And we still want our type system to be as precise as possible. So there already exist approaches for occurrence typing, in particular using constraint solving, but none of them feature type inference. And they are not always as precise as possible when dealing with arbitrary checks. So first, let's define the types that we will use. We will use what we call set theoretic types. So we have the base type, we have the arrow for functions, the product for pairs. But what's interesting is that we can also do the union of two types, the intersection of two types, the negation of a type, and we have the two special types, empty and any, with empty being a type that has no inhabitants, and any being the type of all values. To each of these types, we will associate a set theoretic interpretation. For instance, we will associate to the type false the singleton containing the value false. For the type bool, which can be seen as the union of the type true and false, we associate the set containing the value false and the value true. The interpretation of the negation of a type will be the set of false values minus the interpretation of this type, and the interpretation of a union is the union of the interpretation. Thanks to this interpretation, we can define subtyping. We call it semantic subtyping, and we just say that a type T1 is a subtype of a type T2 if and only if the interpretation of T1 is included in the interpretation of T2. So now let's define our lambda calculus. So we use the usual lambda calculus with pairs and projection. And for the semantics, we use the usual call by value semantics. So we have the beta reduction, the projection on the first component of a pair, and the projection on the second component. For the type system, we will not start from scratch. We will use some usual rules. So we have the rule to type constants, to type variables, the rule for abstraction, and for application. As we have subtyping, we also need the subsumption rule that basically says that if we can type an expression E with type T, then we can also type it with any type T prime that is a supertype of T. And we also use the conjunction rule that says that if we can type an expression E with a type T1 and with a type T2, then we can type it with a type T1 and T2. And this rule is used in particular to type overriding functions. Okay. So now that we have a base, let's try to add type cases and see how we can type them. So we add type cases to our syntax. And for the semantics, it is quite natural. First, we reduce the expression that we want to test. And then once we get a value, if this value is in the interpretation of T, then it reduces to the first branch. Otherwise, it reduces to the second branch. So now let's try to type a type case. So here it's a simple expression. We test whether a variable x is an integer. If it is an integer, we do x plus 1, otherwise not x. So there are two cases where it is easy to type this expression. First, if we already know that x is an integer, because in this case, we know that it will always take the first branch. So we can conclude with this rule that says that if the expression with e that we test has the type t, then we just type the first branch, and the type of the whole expression will be the type of this first branch. The other easy case is the opposite one, when we know that we will always take the second branch. So here, for instance, x has the type bool, and bool is a subtype of not int. So we know that it will always take the second branch. And so we can conclude with a similar rule. If the expression e has the type not t, then you only type the second branch. But what's interesting is the general case, when, for instance, x has the type int or bool. Because in this case, both branches could be taken. So what we will do is to try to get back to the two previous cases. In order to do that, we will use the well-known union elimination rule. So this rule can be applied anytime. And when we choose to apply it, what we can do is to select any subexpression. Here we will select the subexpression x. And this rule allows us to split the type of this subexpression into two separate types and to study each case separately. So here, initially, x has the type int or bool. And we will choose to split it into the type int and the type bool and to study them separately. In order to do that, we replace every occurrence of x by a new fresh variable y, and we try to type this new expression by assuming that y has the type int. And in this case, it is easy because we always take the first branch. And then we assume that y has the type bool. We type it again, and again, it is easy because it always takes the second branch. So with this simple expression, it works well, but let's try with a more subtle expression. Here, initially in our environment, we have a function f. When we give it an integer, it returns either an integer or the value false. And when we give it anything else, it always returns false. And we want to type the following expression. So it takes an argument x. If f of x is an integer, then we return f of x plus 1, otherwise 0. So what's complicated when typing this expression is the first branch. Because we have to remember that f of x is an integer, but we have also to deduce that x has the type int. Why has x the type int? Because otherwise, f of x would have returned false, and it would have taken the second branch. Fortunately, with the union elimination rule, we can make this deduction. The idea will be to apply the union elimination rule twice. We will apply it a first time on x in order to study separately the case where x is an integer from the case where it is not an integer. And then we will apply it a second time on f of x. And in the end, our type system will be able to derive the type any to int, or even better, the type int to int and not int to 0. So let's summarize. Our type system is composed of all the usual rules we've seen in the introduction, plus two special rules for type case that correspond to the special cases where only one branch is taken. And we also have the union elimination rule. And the idea is that the union elimination rule will split the type of the tested expression as necessary, while the two rules for type case will distribute the appropriate split to each branch. We have proved that this type system is sound in the sense that if we can derive the type t for an expression e, then either this expression diverges or reduces to a value of type t. Okay, so we have a type system that is able to type type cases with precision. But what we want is an algorithm, and unfortunately, this type system is not algorithmic. So we will try to make it algorithmic. So in particular, the union elimination rule is not algorithmic, because first, it can be applied anytime. Anytime in our derivation, we can choose to apply this rule. And when we choose to apply it, we have to select a subexpression. Also, we can choose to substitute all the occurrences of this subexpression or just some of them. And finally, we have to choose the decomposition for the type of this subexpression. So the first 3 points makes our type system not syntax directed, in the sense that we cannot deduce, just by looking at the syntax of our expression, which rule we have to apply. The last point requires us to pull a decomposition out of a hat, because this decomposition only appears in the premises of the rule and not in the conclusion. It makes the rule not analytic. So we will fix the first point by using normal forms that will tell us when to apply the union elimination rule. And for the second point, we will use annotations. Okay. So let's focus on the first issue, how to make the system syntax directed. So we have to make decision for each of these points. And we still want to be as general as before. So we want to be able to type as many expressions as we were able to type before. So in order to do that, we will choose to apply the union elimination rule on every sub-expression of the initial expression. Each time we choose to apply it on a sub-expression, we will substitute all the occurrences of this sub-expression in order not to lose information about the correlation between the occurrences. And each time we want to apply it on a sub-expression, we will do that as soon as we can, that is, as soon as all the three variables of the sub-expression are in the scope. In order to help us to implement this decision into the type system, we will transform our term so that it will univocally determine when to apply the union elimination rule. We will call this new form the maximal Turing canonical form, and this is an intermediate representation for the type checker. So let's see how this maximal Turing canonical form works. We start with the example from earlier. And so what we want to do is to apply the union elimination rule on every sub-expression. So for every sub-expression into our initial expression, we will move every sub-expression into a separate definition in order to make it clear that this is a sub-expression and that we want to apply the union elimination rule on it. So we first do that on the sub-expression x+1. We move it into a separate definition. So this bind is a new construct. You can just see that as an alias. It says that u is an alias for x+1. Then we have the sub-expression f of x, but there are two occurrences of it. What we will do is to factorize these two occurrences into the same definition in order to keep the correlation between the two occurrences. And this is the maximal Turing part of the maximal Turing canonical form. We want to share as much as possible, to factorize as much as possible. So it makes a new definition. Then we have the sub-expression v plus u. We move it into a separate definition. And lastly, we have the type case, that is a sub-expression. We move it into a separate definition. And now we can stop because we have only atomic definitions, in the sense that it is only an application between two variables, or type case with only variables. So there are no more sub-expressions that we can extract. So these canonical forms have a syntax. We will say that a canonical form is a sequence of bindings ending with a variable. And each of these bindings associate to a variable an atomic definition. The purpose of all of that is that now the bindings tell us when to apply the union elimination rule. We say that the bindings are the carrier word encodings of the union elimination rule. And so we can rewrite the union elimination rule this way. Only the conclusion has changed. Now it can apply, it only applies on bindings. With this modification, our type system becomes syntax directed. So now let's see this second issue. We still have to choose, when applying the union elimination rule, a decomposition. Actually, the same issue arises also when with the rule for abstraction, because we have to choose a type to give to the newly abstracted variable x. In order to solve both these issues, we will add annotations to the bindings and abstractions. So we can see that in the syntax, and we will see the exact syntax of this annotation later. So each of these annotations will indicate, for a given typing context, the current environment, which decomposition we have to use. We will see that in more detail in a couple of slides, but first, let's see the result that we have. Thanks to the maximal Turing canonical form and the annotations, we can define an algorithmic type system based on the initial type system, but where the union elimination rule only applies on bindings and reads the annotations to determine the decomposition. And we have proved that this type system is sound with respect to the initial one, but it is also complete. So the completeness means that if we can type an expression E, if we can derive the type T for an expression E with the initial type system, then we know that there exists some annotations to put on the maximal Turing canonical form of E, such that this newly annotated expression is typable with the algorithmic type system. And this gives us a new way to determine whether an expression is typable or not. If it is possible to annotate the maximal Turing canonical form of an expression so that it has some type by the algorithmic type system, then we know that it was typable with the initial type system. And otherwise, we know that it wasn't typable. So now, naturally, the new problem that we want to solve is how to infer these annotations. So first, let's formalize these annotations. So basically, an annotation is a set of pairs gamma t, with each pair gamma t, meaning that if we are under the typing context gamma, or a typing context refining gamma, then the type t must be part of the decomposition that we will consider. So for instance, in the following expression, the annotation means that under any environment, the type that we must consider for the decomposition of x are the type int, not int. So now let's try to infer these annotations. So unfortunately, we do not have any complete algorithm for that. But we have some heuristics. What we will do is to start by annotating every binding and abstraction with the most general annotation, which is the annotation that associates to any typing context the decomposition any. And then what we will do is to iteratively refine these annotations until we get something typable, or until we notice that it will not be typable. In order to do that, we will look at two things. First, we will look at function applications. So here, for instance, we have the sub-expression x plus 1. And we know that this is only typable if x is an integer. So what we will do is to refine the annotation of x in order to study separately the case where x is an integer from the case where it is not an integer. Then we can update the annotation for u, because we know that u is only typable in the case where x is an integer, and in this case, u is an integer. And we do not want to decompose it further. Then we can update also the annotation for v. Okay. Another thing we will look at when refining the annotation are the type tests. Here we test whether v is an integer or not. And so we will update the annotation for v in order to study each case separately. Then we can update the annotation for w and for z. And now we are done. This expression becomes typable by our type system. And in order to type, now when our type system will try to type this expression, it will look at the decomposition we found for x, and so it will study separately the case where x is an integer from the case where it is not an integer, and thus it will find the following type, int to int and not int to 0. So let's finish with an example that you can test online on our prototype. So we first define two types, the type falsy that contains the constant false, the empty string, and 0, and the type truthy that contains all the other values. Then we can define this function not. It tests whether its argument x is truthy. If it is truthy, it returns false, otherwise true. In order to type this precisely, our prototype has to find the right decomposition for x, and it will do that by looking at the type tests. As we test whether x is truthy or not, it will choose to decompose the type of x into the type truthy and falsy, and it will give this type, which is the most precise type that we could find. We can also define the function typable just by applying 2 successive times the function not to x. And this time, in order to find the right decomposition, our prototype will look at the application not x and deduce that it also has to decompose x into the type truthy and falsy. Now we can combine both mechanics and define this function end. This time, in order to find the decomposition for x, it will look at the type tests. And in order to find the decomposition for the variable y, it will look at the function application typable y. And again, it will find the most precise type possible. And we can also define the function r just by combining the other function. And again, our type system is able to infer the most precise type. So in conclusion, we provide a simple and generalized type system for occurrence typing. And we prove that finding a typing derivation in this type system for an expression E is equivalent to finding some annotations for the maximal Turing canonical form of E. Also, we provide a sound implementation where finding this annotation is based on time tests and application of overloaded functions. And we're working on some future work. We want to add polymorphism to this type system and to support side effects. And also maybe we're thinking about mixing gradual typing and occurrence typing. Thank you everyone for your attention.
Thank you. So we have some time for questions. Are there questions? Here.
I missed the very beginning of this, but just to clarify, can you type anything as any to any? And if so, what effect does this have on the strength of the kind of annotation? Actually, no, scratch the second part, just first thing.
So you ask if we can type any function with the type any 20? Well, we could do that. If the function is well typed, then we can always type it. No, I mean, no, we cannot type every function with the type any 20 because only the functions that can take any type of argument can be typed by any 20. Yes. So the support type of every function is not any 20, but empty 20. And so every function can be typed with the type empty 20. But this type is not very useful because then we cannot apply the function anywhere.
But like, what about, for example, say the subfunctions? Like, assuming you're allowed to change the annotations of all the functions which appear in the function. If you did it like, completely recursively, say you could change. Like, assume you did it kind of recursively. So like, if I have lambda x dot f of x, I'm also allowed to, change the annotation of x, assuming all the definition of f, assuming all the definitions are transparent. I'm just trying to understand the system.
So, what is your question exactly? Sorry.
So, like, assuming that all the definitions in the system are transparent, and forgetting about primitive operations for a second, can you type anything as any to any? Because you were talking about you mentioned gradual typing on the slide, and I was just wondering if this was a good base case for gradual typing, since empty is a bit of a weird base.
I mean, no. The type empty is not like the Joker type for gradual typing. The Joker type for gradual typing means that you can type everything with the Joker type, but then you can use, if you have a function that takes the Joker type as input, you can apply it to everything. In our case, if you type, if a function you type it with empty 20, you can apply it to nothing. So it's not, the Joker type is not the same as empty type.
Okay, let's move on to a question from the remote audience. Can you put that up? Oh, okay. So I'll read it out. And so this question is from Paul Zhu. He asks, an interesting new approach for type inference, union types. Can it be applied to languages with generic types, typical in OO languages, such as Scala?
That's a good question. I haven't thought about it. So with generic types, actually, I don't really know. We can type. I mean, we can always represent a generic type with the type any, but then we are not precise when we want to reuse it. Yes. Oh, yes. Okay. We want to add polymorphism. Yes. If it is what you call generic types, yes, we want to add the polymorphism.